Alright, welcome back. I trust that you did well on the quiz that you took today. And we're going to look over page 373, 24.4. That's going to be 24.4, and we'll work over 24.4, 24.5, and even 24.6 today. We'll kind of capstone the rest of this chapter, chapter 24. And so with that discussion, we'll start with something kind of from chemistry. But if we're going to understand current, we have to talk about this. And so it says conventional current is not used as common practice in chemistry as it is in physics. Because this section relates chemistry to physics, we will return to the discussion of current as the flow of electrons. And so now, instead of using Q pluses, we're going to be looking at E minuses. I mentioned earlier that for physics we used positive conventional current. It's convention, it's what we choose. And then in chemistry it looks more at the negative charges that are moving. So, what is an electrochemical cell? This particular slide says an electrochemical cell produces electrical current through chemical reactions. That's pretty simple. So electrochemical, so electrical things through chemical reactions and cells that contain them. What is the basic component of that? Well, you're going to have two electrodes. Those are metal strips that sit inside of an electrolytic solution. The electrolytes are charged particles, ions, usually things like K+, sodium plus, Cl-, those types of things. Those are electrolytes. Those are the things that give a liquid its ability to carry charges or electrons, and then something called a salt bridge as well as wires. And so each one of those things is defined on 373. Of course, the whole point of an electrochemical cell is to produce electricity that can do something. And so the piece that's attached to it is called a load. You'll notice on 373 there's a light bulb, and that is the load. And then there are two different, I mentioned the electrodes. There's two electrodes. I'll mention these now. Let's look at this one and the other. That is the anode and the cathode. And I'm going to talk through these kind of at length in just a moment. But remember, the anode loses electrons and the cathode gains electrons. Because of that, you remember from chemistry the statement oil rig. And so the statement is oxidation is lost. Loss of what? Electrons. And so this is part of oxidation, and then reduction is gain. Gain of what? Electrons. And so there's one side that is reduced and one that is oxidized, and we will look at those in half reactions in just a moment. But those are the two electrodes. One is called the anode, one is called the cathode. Alright, let's look at this particular picture. You'll notice the half reactions. The main reaction's not visible to us, but we have zinc. Zinc is producing, notice the zinc is turning into a Zn2+ ion, and it is giving off 2 electrons. Okay, maybe you will recall this, whether or not you do. The statement is an ox and a red cat. Okay, so the oxidation happens at the anode, so that's oxidation, and reduction, sorry, I'll do it the same way, cathode is where reduction happens. Okay, and again, you need to know this statement, oil rig. This is part of a redox reaction from chemistry, oil rig. And so oxidation is the side that loses electrons. So if you'll notice on this side, you'll notice that electrons are lost. They are given off in the half reaction. So this is the oxidized electrode. And then over here, obviously, if that one's oxidized, then the reduced one will be the copper. So this will be reduced. But remember, oxidation is loss, reduction is gain. And so you'll notice you have copper 2+ that is gaining 2 electrons as the reactants, and it will become a neutral copper. And so this is the gain of electrons. We will call this reduction. So this is reduced. So an ox and a red cat. So you will notice that an anode oxidizes. So this must be the anode. And the copper is the cathode because it is reduced. And of course you've got the other parts that are important. Notice the salt bridge here that is allowing certain solvents to go up and be transferred. Notice the electrons I mentioned in the anode are being lost. You'll notice they are choosing to go this way. Now notice we're choosing to look at electric current. Now electrons rather than Q pluses. Q plus would actually be going this way. It would always be opposite of electric current. And so that's what we're talking about. Okay, again, you've got these important terms. You've got the electrodes. There's two of them, anodes and cathodes. So you'll see the cathodes down here. This cathode is here, and the anode is here. You'll also notice this is all part of an electrochemical cell. Of course, none of this would be possible without the fluid electrolyte. This needs to be something that can carry the ions of zinc 2 plus and copper 2 plus inside of it. And then, of course, we've got the salt bridge. It mentions that a porous material soaked with a suspended aqueous solution to allow the ions to travel. And then, of course, the load. The whole point of this is that you create electron flow. If you create current, you're going to do something with that current. You're going to produce light. You're going to produce motion. You may put it into a generator, a motor, whatever, and do something with it. But a light is going to be a simple one. Okay, so that is those are the components of an electrochemical cell. All right, moving on. EMF depends on the chemical reactions involved, and this will be found on the small paragraph on the next page, page 374. It says the EMF, the electromotive force, the potential difference, the voltage depends on that. It mentions a combination of two or more electrochemical cells is actually called a battery. And so when you look at a normal AA, we'll call that a voltaic cell. So the simple cylinder. You've got this disc like so. Looks more like a AAA, what I'm drawing. Of course, you've got the little nub on the end of it. This end, of course, is the positive. This end is the negative. We'll call it a AAA. Okay? And so this particular battery, we use the term battery, but it is not a true battery until you put a second one on the end of it, because a battery is a combination of electrochemical cells. And so that's what we mean when we use the term battery. Okay, so a AA, quote, battery is not actually a true battery according to physics definitions. All right, so there are some that would actually be that. It says a larger cell can, however, furnish more electrons, but we will talk more about that later. It's possible. All right, so there's two types of ways to arrange cells. I'm sorry, I was looking at 374 when I was reading this section here. It says size AAA, AA, C, and D batteries, quote, batteries, are individual electrochemical cells. They are not batteries until they are combined in some appliance. This is not to say that all batteries are just electrochemical cells. For example, a 12-volt car battery and a 9-volt battery are actually true batteries because of the way they work. So that's the one statement I wanted to make. All right, there's two ways to arrange your batteries or your electrochemical cells when you set them up to be used. The first way is in series, and so what you simply do is you set them up positive to positive, positive to negative, positive to negative. So you'll notice here at the bottom I'm simply taking my batteries, I'm taking the negative side, I'm attaching it to a conductor, and I'm connecting all the positives to a negative, positive to a negative, positive to a negative, positive to a negative. That creates what we call series. The whole point of series is that the current must go, notice the current of electrons must go through every single one of these in series in order to go to the load. Okay, that would be the purpose of using cells in series. And so it says the voltage, if you ever need to find the voltage, it's actually, for cells in series, it's the sum of the voltage for all of the cells. So trivia for the day, AAAs and AAs all have 1.5 volts. And so here you go, there's 1.5 volts here, there's 1.5 volts here, 1.5 volts here, 1.5 volts here. That's 3, and that's 3. And so the total of the voltage for the entire circuit is 6 volts. You'll notice that at the voltmeter or at the load there. You'll have all of the voltage all the way across. The current, however, is limited by the smallest cell. And so it depends on the ability of the current that's produced. All of these can usually hold, it mentions in your book, about 0.25 amps, and so it's based on the lowest one. So if you have a weak battery, your cells are only as good as your weakest link. I guess I could say it that way. But the current is limited. That is to be contrasted. I'll give you a second to think through that. There are actually two questions at the end of the chapter. I believe they're questions 8 and 9 that require you to know this. And so I would actually recommend that you go and do 8 and 9 at the end of this chapter after this lesson. Technically, it's the homework assignment for this, but you would really ought to go very quickly before you forget. Okay? So that's cells in series. Notice they're one after another. For cells in parallel, notice the pictures. That's in series. This is in parallel. This is going to be positive to positive to positive. So in this case, we have a conductor. We connect it from here to the positive, to another positive, to another positive, to another positive. Now, The negatives will be, of course, attached to negatives, to negatives, to negatives, and all the way across we have it. That's cells that are parallel. You'll notice another bonus feature to this is that the wires actually look like little rectangles, and if you know your geometry really well, then of course these are parallel to each other, and opposite sides would be parallel. Cells in parallel, the two rules here, you're really kind of relating the voltage and the current. In a parallel circuit of cells, electrochemical cells, the voltage is the same as the individual cell voltage. So let's say this one has 1.5 volts, this one has 1.5 volts, this one has 1.5 volts, 1.5, and this one has 1.5 volts. The question would be, and if I put a load somewhere in here, a light bulb, because it has to do something, there would be no electromotive force if it's not a complete circuit. The question would be, how much voltage is in the entire circuit? Well, it says the voltage is the same as the individual voltages. So the voltage total is actually equal to 1.5. It's the individual ones. 1.5 volts throughout the entire system. So in series, it would be a total of 6, but so this would be series, and this would be parallel. Okay. Now going down here, so that would be the answer if it were in series. The current is the sum of the individual currents of each cell. And so giving an example of that, you might produce, let's say, 0.25 amps of current in each one. Sorry, I'm trying to erase this. And so going through, I might create, current is the sum of this. So this has 0.25 amps of current. This one has 0.25 amps of current that it produces 0.25 amps of current, 0.25 amps of current. And so I was using the number the book gave. Is the sum of the individual. So amp total, okay, many times we actually use I for this, for current. So I total is equal to I1 plus I2 plus I3 plus I4. Well, they're all the same, so you could say I total is equal to 4I. Okay, and so the I of each one is 0.25, and if I understand that right, that's 1/4. So I total is equal to 1 total amp going through the entire circuit. So that's how that works in doing one of these. And again, that number 8 and 9 will also be very helpful to you from the homework. All right, so that's electrochemical cells and kind of how they work. Now look at the pictures at the bottom of 374. Make sure you understand what's going on with those pictures. That changes our topic slightly to the concept of thermoelectricity. Now, this topic is fascinating to me because what they do is they actually take two different materials. Your book actually does a good job. So you kind of have a particular metal that is a conductor. They put it a little sleeve on it, and they make it kind of do a loop, and it's got a different metal. This is exposed, and this particular end is cold, and this particular end is hot. And apparently, on hot ends, you have an excess of really excited molecules, and they really want to go somewhere. And then on the cold end, they kind of don't really care what they're doing. And so there actually seems to be, because of the excitement in the electron flow, the electricity actually will start to flow because of the excitement of it. And so you actually can get a flow of electricity. Now, what they end up doing is they actually can make a big thing called a thermocouple, and they can actually take two of these wires. You'll see that at the bottom of the page there, 375. And by the way, they mentioned one of the wires is copper, one of them is iron. You can get some different things to flow. You'll notice in the middle picture you have two of them that are made of copper, and interestingly, all of them excitement goes towards the top, but in 24.29, the bottom right picture, you'll notice a cycle. The actual current will cycle through that wire. So thermoelectricity is interesting. The application of that directly is this concept of a thermocouple. It's a complete circuit in which two conductors made of different materials come together. So we're thinking about iron and copper for the example there. And you maintain a different temperature. In order to do this, you must have different temperatures. And I wanted to mention these two terms. It mentions these on page 375, the Seebeck effect, basically. Seebeck is named after Thomas Seebeck in the 1700s, early 1800s. The man, he mentioned this. The magnitude of Seebeck voltage depends on a couple factors, and so let me mention these real quickly. Seebeck voltage is the potential difference caused by the differing temperatures. So potential difference is the same thing as voltage. Let me point these out for you. So First of all, you can create electricity apparently with two conductors that have different temperatures, and so you get what's called Seebeck voltage. It's a potential difference or voltage caused by different temperatures. Now, it separates that from what's called the Seebeck effect. This determines the magnitude of the voltage depending on two factors, and these you'll see these on the bottom right of 375. The extent to which the materials differ in characteristics, so iron and copper both have different characteristics, they can't be the same one, and then of course the temperature, the hotness or coldness of the two sides, and so thermoelectricity is interesting. I wanted to mention this person, this name is Peltier, some people say it Peltier, but it mentions this on page 376 of your book. It says, the Seebeck effect is reversible. If a current is sent through a thermocouple, heat is formed at one junction and absorbed to the other, the result being a temperature difference between the junctions. The heating or cooling of a junction between two dissimilar conductors is called the Peltier effect. So there you go, there's your definition. The heating or cooling of a junction between two dissimilar conductors. This is the basis for refrigerators and heat pumps. They use what's called a thermocouple or even a Peltier module. And so in the description, I'm actually going to put another link to a video. That particular one is going to be really cool. It was one of my first times I ever got to see this. There's a video of someone who makes an iPhone phone charger using a candle. They heat one side of this Peltier module they got off of something, a refrigerator or something. They heat the bottom of it, and it starts to form an electric current. The difference between of the temperatures creates electric current, just enough to charge a phone with a candle. So, you know, if you ever need a candle, if you ever need to charge your phone and all you have is a candle and a Peltier module, you can use this to your advantage. 376, changing topics a little bit, we talk about what's called, okay, I'm going to do my best here. I understand the best I can say this is piezoelectricity. I've heard people say piezoelectric, but I believe it's piezo. And so piezo means to press or pressure. So pressure electricity. Pressure deforms a crystal, and stress creates a potential difference. Now, apparently there are piezoelectric crystals out there that can produce electric current just by pushing them. I found out, interestingly enough, that these particular crystals exist in those little lighters that you can get at the dollar store. Kind of have a little gun trigger on them, so you pull them and you have to push the thing that allows the flames to come out, and you push the little trigger and you'll hear and you'll kind of hear it pop. Another example is actually they use these piezoelectric crystals on the push switch for a gas grill. So it's a little red button. When you push it in, you'll hear it go and it'll put a little spark in and it'll ignite that propane, and you'll kind of see that there. So piezoelectric crystals, if you ever open up those $1 lighters, you might even notice those. That actually, it might be worth opening up a lot of things just to understand them, but those things are really fascinating. You'll also notice towards the end where the fumes come out that there is a little metal triangle that's facing towards it. I think I can draw this. First of all, I think you know what I'm talking about, but I'm talking about the lighters you can go buy at the dollar store. They kind of have an interesting handle, kind of have little place for your hand. There's a little button that kind of sits right here, kind of your button. And so then over here you kind of got this, and then it's kind of got this end over here, and it kind of comes out into a place where the flame, you know, comes out of it, and then kind of looks like this. For the most part, that's an almost perfect picture. Of course, usually there's a little line over here that lets you see the fuel on it, but there's actually right about here, there's a little triangle that bends inward. And remember, electrons concentrate right here. There's a little tube that goes inside. Fascinatingly, the tube goes through the inside, coils around, goes in here. The piezoelectric crystal's here, so when you push in the button, you put just enough pressure on the crystal, it charges this, and the electricity forms on that triangle, sparks the gases, and you got a flame. Okay, and usually there's kind of like a little air intake on the side of this as well. And so pressure deforms this crystal on your grill. When you push in that igniter plug, you will also have a spark that's generated. So also a voltage on a crystal can cause them to deform and vice versa. So that concludes this particular lesson. I would take a moment, even before you forget, to look at the problems 8 and 9 at the end of the lesson. But I will see you when I get back. And actually, before I close this, your teacher, your proctor, and you will go through some of the math lessons from the chapter. I mentioned on Monday that you all would have a test on Tuesday. I realize you all have a field trip on Monday, and therefore your test will actually be on Wednesday after we get back. But with all that being said, I will end the lesson here. Thank you.